The formation of our solar system stretches back approximately 4.6 billion years, captivating both scientists and curious minds alike. This epic journey provides a framework for understanding the formation of countless other planetary systems scattered throughout the cosmos. The tale of our solar system is one of gradual assembly shaped by gravity and cosmic chemistry set against a youthful universe. By studying the solar system's origins, we gain insights into planet formation and the potential for life elsewhere in the universe. Each planet, moon, and asteroid holds clues to the conditions that prevailed during the solar system's infancy. Understanding the solar system's formation also has practical implications for space exploration and planetary science. In this essay, we will journey through the stages of the solar system's formation, from the initial collapse of a vast nebula to the ignition of our Sun and the subsequent assembly of planets. The Nebula hypothesis stands as the cornerstone theory explaining the formation of our solar system, proposed by astronomers like Immanuel Kant and Pierre-Simon Laplace. This hypothesis suggests that the solar system began as a vast cloud of gas and dust, known as the solar nebula. Its gravitational collapse initiated a series of events that would ultimately lead to the creation of the Sun and the surrounding planets. Central to the nebula hypothesis is the concept that the solar system formed from the remnants of a previous generation of stars, enriched with heavy elements through stellar processes. These elements, formed in ancient stars, were scattered into space by supernovae, seeding the nebula with the building blocks necessary for planet formation. As the nebula collapsed, the conservation of angular momentum led to its transformation into a spinning protoplanetary disk. At the center of this disk, material concentrated to form a protostar, which would become our Sun. Surrounding this hot, young star, the remaining cloud material flattened into a disk, setting the stage for the birth of planets and other celestial bodies. The transformation of a nebulous cloud into a structured solar system is a tale of cosmic choreography. Our solar system began with a nebula collapsing due to gravity, possibly triggered by a supernova. The central region grew denser and hotter, forming a protostar. A rotating protoplanetary disk emerged, composed of gas, dust, and ice. Tiny particles collided, forming planetesimals. These evolved into protoplanets. Rocky planets formed in the inner disk. Gas and ice giants emerged in the outer regions. The Sun's ignition dispersed the remaining gas, leaving a structured system of planets. Approximately 4 billion years ago, the solar system underwent a dramatic phase known as the Late Heavy Bombardment, or LHB. During this period, a sudden surge of asteroids and comets bombarded the inner planets, leaving a lasting impact on their surfaces. The LHB represents a pivotal epoch in the solar system's history, reshaping planetary surfaces and possibly influencing the conditions for life on Earth. The causes of the LHB are still debated, but it is widely believed to be linked to the migration of the giant planets. As these massive bodies shifted orbits, they disrupted the orbits of countless smaller objects, sending them careening towards the inner solar system. This influx of impactors collided with terrestrial planets, creating craters and altering geological features. The LHB played a crucial role in shaping the young Earth's environment, potentially delivering water and organic compounds necessary for life. Similar processes likely affected the Moon and other nearby celestial bodies, leaving a record of cratering that we can still observe today. The solar system is a diverse assembly of celestial bodies, each with its own unique characteristics and histories. At its heart lies the Sun, a G-type main-sequence star, primarily composed of hydrogen and helium. This massive ball of nuclear fusion provides the energy and gravitational anchor for the solar system, around which all other objects orbit. The planets are classified into 3 categories based on their composition and location within the solar system. The terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky and located in the inner solar system. Beyond the asteroid belt lie the gas giants Jupiter and Saturn, which are primarily composed of hydrogen and helium. Further out, the ice giants Uranus and Neptune are composed of heavier elements like water, ammonia, and methane, giving them their distinct bluish hues. In addition to planets, the solar system contains a variety of other objects, including moons, dwarf planets, asteroids, and comets. These bodies contribute to the dynamic and ever-evolving nature of our cosmic neighborhood, each playing a role in the solar system's gravitational ballet. The solar system's formation is but a small chapter in the grand narrative of the universe, which began with the Big Bang approximately 13.77 billion years ago. This monumental event marked the creation of space, time, and the initial elements that make up our universe. From this primordial explosion emerged hydrogen and helium, the lightest and most abundant elements, which later served as the foundational building blocks for the solar system. As the universe expanded and cooled, these elements clumped together under gravity to form the first stars and galaxies. Within the cores of these stars, nuclear fusion forged heavier elements, such as carbon, oxygen, and iron. When these stars exhausted their nuclear fuel, they exploded as supernovae, dispersing these enriched materials into space, where they eventually coalesced into new stellar systems. The solar nebula, from which our solar system formed, was a product of this cosmic recycling. The presence of heavier elements in the nebula attests to the generations of stars that lived and died before our sun was born. The story of our solar system's formation is continually enriched by new discoveries and technological advancements. Modern research reveals the complexities of planetary formation in other star systems. Missions and telescopes provide data seeking the birthplaces of new solar systems. Ongoing research refines our understanding of the solar system's formation. Scientists use simulations to model planetesimal collisions and planetary migration. The search for exoplanets reveals the diversity of planetary systems. Discoveries of Earth-like planets challenge our understanding of habitability. The journey from a nebula to a structured system inspires us to understand our place in the cosmos.